Can you hear me? Okay, thank you very much. So I will send you an email for possible Q&A session today around 5 p.m. for the صباح النور, for the extra material that I sent recorded for last week. And now I will continue with the slides for part 3. If you have any questions, send me in the chat box, or when I ask you for if you have any questions, you are welcome also to ask the question in person. Okay. Now we will try to all be on mute so that we do not make too much noise, so we can all hear very well. And try not to use your video because your connection will be weaker. Okay, so I will start the session. Okay, so the last section of part 3 discusses improved current sources. يعني نحن we studied a current source to bias the amplifier, and we saw that it has an effective load resistance, and it puts some constraints or requirements on the range of the voltage so that the amplifier and the current source remain in the saturation mode. BJT, as we will see next, there was an error turn. So what happened is that people did some more effort in order to improve those current sources so that the load will be reduced, يعني resistance, effective resistance will tend to infinity, become current very large, like the ideal current source. And also, so عم نحاول نكبر الاوتبوت resistance ليصير قريب للايديال اللي هو infinite. And also maybe make it less dependent on beta. And instead of having an error term of being 1 over beta, the error term will become even smaller. And also it will allow me to operate in a larger voltage range. And we would like to operate between 0 and VDD. So without risking the operation of the amplifier, keeping the amplifier in saturation. But we will see sometimes we have to pay a trade-off, so things will maybe degrade from one side and get better from the other. So the first and most based current mirror is called the cascade current mirror. Now we studied the regular current mirror, and it really looked like the lower half. يعني the regular current mirror had two transistors, Q1 and Q2, and it fed my circuit. Now what they said, exactly just like I had two transistors stacked to do the amplification, I can also have two transistors stacked to make the current mirror function. For our purposes, when we see something like this, if I have I reference and it is feeding into two diode connected transistors instead of one, okay, and then on the other side I have two transistors that are mirroring the current, immediately what I can do is I can assume that this point is a DC bias for purposes of my circuit, and this point is a DC bias for purposes of my circuit. So practically speaking, the effective resistance of this current mirror, which is mirroring I reference, so I'm saying I reference here because these are sharing the same VOV or the same VGS, okay? And the same current that is flowing because of KCL in those two transistors here, it is also flowing in those two transistors because these share the same VGS. And then there is no other place for the current to flow, so the current in Q2 will flow in Q3. But the difference between this and the regular current mirror is that now I have two stacked transistors that are supplying me the current, okay? And those two stacked transistors have DC or ground at their gates. So their effective resistance, the effective resistance is that of the cascade, which is that of the RXY. And because it is that of the RXY, I have a product of a gain times RO. So I am no longer only seeing in the regular current mirror, I used to see an effective resistance equal to RO. Now in this big current mirror, which is still supplying the same current, I see a larger resistance. نحن إذا عندنا ideal current source, typically we say that its resistance, if it is ideal, is infinite. Now it is not little RO, it is not infinite, but it is a number that is larger that is in between. Okay, so this is the cascade current mirror from a resistor perspective. Anybody has any questions about the current mirror resistor? Okay. So the next thing that we worry about now, it provided me with the current. It has DC bias at Q2 and Q3. I know its resistance. The next thing that I look for is really, well, what is the allowed voltage swing for V output? يعني أنا if I have my amplifier sitting here, okay, if it is feeding my amplifier, which is sitting here, and the amplifier is between VCC and V out, okay, this will be constrained from one side by the amplifier, which we don't want to worry about now, and from the other side it has to maintain that this circuit here is operating, the two transistors are operating in saturation, so that they will share the same VGS here, and therefore they will have the same current if they are in saturation because they have the same VOV. So let us look at now the shared voltage, what it is. So if we look at VG3, okay, if this is gate 3, we know that gate 3 is equal to this voltage from here to here, okay, and then from here to here, right? So this is VG3 is really VGS4 plus VGS1, okay? So if VG3 equals VGS4 plus VGS1, which is VGS2 basically, okay? Each one of these is nothing but VOV plus VT, okay? So this is VOV plus VT, and the same for this one because the same current flows in them. So across Q4 and across Q1, they both operate with the same VOV because the same current flows through them, and their VGS is equal to VOV plus VT. So VG3 is equal to VGS4 plus VGS2, which is equal to twice the VOV plus VT, which is 2VT plus 2VO. This is this voltage here, VGS. Now, if I want to say what is the minimum operating output voltage, I will say for transistor Q3, okay, I have a requirement which is I want VDS3 to be greater than VGS3 minus VT, greater or equal. Okay, this is from the regular saturation condition. Okay, this is from the regular saturation condition. Now, I know what VG3 is. Okay, so VDS3 is really VD3 or VO minus VS3. And I want this to be greater or equal to VG3 minus VS3. Okay, minus VT. So now, if we want to cancel VS3 from both sides, we end up with the constraint that we want VO to be greater or equal to VG3 minus VT. But this quantity here, I have already calculated it before from the VOV of this transistor and this transistor. Okay, so therefore, I know that the minimum VO is equal to VT plus 2 VOV. Okay, so then I get from this and this, I get that VO minimum has to be equal to VT plus 2 VOV. So who cannot hear me? Marianne, you cannot hear me? Marianne? Anybody has any questions meanwhile? Okay, great. Okay. So, okay. So let us now then move on to the next slide. And basically, the idea is that now we will see that this has a large output resistance, and also it has now a constraint on VO. So قبل كان ال VO related to VOV alone. Now صار عندنا twice VOV لأن عندي stack of two transistors. So the range of operation of VO صغر, it became smaller. يعني VO cannot go below this value. So if I draw on the scale of VO, if this is VO, now VO cannot go, if it is fluctuating, below the value 2 VOV plus VT. Okay, that's the constraint or the trick here, because قبل كنا constrained by 1 VOV, هلا صار هيدا forbidden range. I have to operate at a voltage that is higher than 2 VOV. Okay, لأنه حطيت stack of two transistors. Okay. Okay, so Ryan, I will repeat how we got the VO. Let me erase the ink. So what we said is that for VG3, did you catch, Ryan, that VG3 equal to VT plus 2 VOV? Okay, so VG3 is equal to هيدي الجيت 3. It is equal to VGS here. It is equal from this node to this node. It's equal VG3 to VG1 plus VG1 to ground. Okay, plus this to here. Okay, now VGS4. So VG3 equals VGS4 يلي هي هيدا البورشن plus VGS2 يلي هو هيدا البورشن by KVL لأنه هيدي اللوب. Okay, now we know since each one of these transistors قطعة في IRF that its VGS is equal to VOV plus VT. Okay, طيب ما it's the same applies for VGS2. It's also VOV plus VT. Okay, therefore VGS4 plus VGS2 هي 2 VOV plus 2 VT. Okay, هيدا given from VGS from VG all the way to ground. Now we say we want Q3 to be on set. Okay, so when we say that we want Q3 to be on set, this means that we want VDS3 to be greater than VGS3 minus VT. Okay, بس أنا بما إنه S is common فيني أقول يعني this translates that VD3 be greater than VG3 minus VT لأن هن عندهم نفس الأس. طيب بس VG3 أنا I know that it is 2 VT plus 2 VOV. أوكي، so حأطرح منها VT هتصير هاي الكوانتيتي اللي هون هي شو؟ هي equal ل VT plus 2 VOV. Okay, so it's equal to VT plus 2 VOV. Therefore we want VD3 هي VO يكون أكبر من VT plus 2 VO. Okay. Okay, thank you very much. Okay, so we're going to jump now to the next slide. You're welcome. About the BJT. The BJT, the standard current mirror that we studied before, we said that those two transistors, I have here a diode connected to the transistor. Those two transistors share the same VBE. Therefore, they will have the same IC flowing in both sides. But then we said my IC is really my IO. However, I reference اللي جاي على هيدا الترانزستور في عندها a factor of IC plus 2IC over beta لأنه هاد two currents جامعين بالI reference. So therefore I have an error term اللي هو 2IC over beta و IO على I reference are differing by this term. This is the traditional approach and the error is proportional to 1 over beta. So the designers said, we want to get rid of this term or make it smaller. The key to them in the beginning was to reduce the error coming from this branch. So هيدا الشيء helped them to reduce the error to be 1 over beta squared. يعني if my beta is 100 بدل ما يكون error 1% حيصير error proportional to 1 over 10,000. Okay, so let us see. What is different between those two circuits? بعد ال IO equal IC, they are still sharing the same VBE. IC is flowing here. وهيدا البرانش, it still has, like here, 2IC over beta. So this branch still has 2IC over beta. What differed is that I made a breakpoint here. I injected a transistor BJT here. And now, instead of passing the emitter current of the BJT directly to IC, what happened is that I am passing now the current of the base. Okay, so whatever is here in yellow to IC على بتا حينقسم بعد بشو بفاكتور equal by بتا plus 1. Okay, وهالشي مضروب ببتا بالدينومينيتور حيصير proportional ل بتا squared بيصغر الايرور of I reference. هلا we will see it on the next slide. So basically, instead of passing the 2IC over beta directly to I reference, I am injecting a BJT that is shielding me from the 2IC over beta and dividing it further by beta plus 1. So now the term I reference بدل ما يكون بس 2 على بتا مثل ما كنا شايفينه قبل, now it has another term here. Let me just put the highlighter. Now it has another term here which is beta over beta plus 1. يعني هيدا الترم صار كله كمان عم نقسمه by beta plus 1 يعني صار فيه beta squared. Okay, so now IO over I reference has an error term which is proportional to 1 over beta squared, and therefore I managed to reduce the error to a very small number. Okay, so حدا عنده سؤال على هيدا الامبليفاير على هيدا current source? Okay, so for this one, what is the condition on V output? Here, V output is still the condition on V out is still that we want VO. Sorry, let me put the red color. We want VO to be which is equal to VCE2. اوكي, هيدا بعده مثل القديم to be equal to VCE2 بدنا اياها تكون اكبر من 0.3. اوكي, ما تغيرت. والاوتبوت ريزيستنس اذا اعتبرنا انه هيدي النقطه هي دي سي لانه هيدا كارنت ميرور مثل ما كنا نعتبرها قبل, كمان is equal to little arrow. اوكي, this is equal to little arrow. اوكي, there are other types of current mirrors that try to enhance the maybe output resistance. Okay, so they try to enhance the output resistance by stacking two transistors on top of each other. Okay, so always if I want to benefit on the output resistance, I'm going to stack two transistors, but I will lose on the voltage range. So let us look at this circuit here without too much analyzing into the numbers. These are sharing the same VB. E, so they have the same IC here. هيدا البيز current IC على بتا IC على بتا, so this is 2 IC over beta. Now the current that is flowing here هو جمع ال IC مع 2 IBs, but this is IE of Q3, so this is IE3, okay? So what is happening now is that here I am seeing IC3, okay, which is approximately IC plus the base current, بس مقسوم على plus the base current, sorry. And on this side, هيدي ال IE3 شو عم بيصير فيها؟ عم تنقسم، عم تصير IB، يعني عم تضعف، عم تنقسم هون على بتا plus 1 و IB3. Okay, so the error term عم يصغر مرة تانية without digging too much into the details. So I'm starting with IC plus the base current. عم ببعتها على البيز هون تاعون 3 عم تنقسم على بتا plus 1. عم بصير ال I reference هو عبارة عن IC plus term صغير plus a small delta here. Okay, وال IO كمان عم بصير IC plus some other small term, يعني بتا على بتا plus 1 فينا نعتبرهم راحوا, فهيدا فيه error term. The people who derived the full equation, they came up with this complex equation, which they later proved that it is approximately proportional error ل 2 على beta squared. So what really matters for us here is that we know and those two share the same VBE, they have the same IC here, and then we're shrinking the error by passing it to the base of Q3, ليروح على I reference. So حسنوا ال error term. Now, let us see what happens now if we are trying to look at the other terms اللي هن ال output resistance. كمان ما عملوا لنا derivation لألن هون, بس عطونا إنه it is beta over 2 times some RO, لأنه في عندي stack of 2 transistor. بما إنه beta is around 100, I don't see little RO anymore. I see large resistance because of the stacked devices. Okay, and then if they ask me about what is the VO minimum for this circuit, the VO minimum is composed of satisfying two criteria. أول شيء إنه Q2 يكون بالأكتف, يعني هيدا الفولتج اللي هون يكون أكبر من 0.3. Okay, and then the other thing is that here VBE for this transistor ليكون on, بدها تكون قديش هيدا الفولتج؟ بده يكون هيدا 0.7 volts. So total from here to ground, I will end up with 0.3 volts plus من هون لهون. هيك لأعمل لكم highlight لها لأنها بطلت مبينة. I'm going to erase this and I'm going to highlight it with yellow. If we look from here to here, I have 0.3, and then from here to here, okay, I have 0.7. So حيصير مجموعهم هيدا short circuit is equal to 1 volt. So VO minimum is going to be equal to 1 volt. Okay, so let us write it again. So this requirement here, I have to have this 0.3 هون فولت, وهيدي بدي اياها تكون 0.7 ليقدر يدور هيدا يكون هو good VB. Okay, anybody has any questions about VO minimum for this circuit? Okay, so this is thank you, Marianne. This is another type of current mirror where we enhance R. We reduce the error, but we get a penalty on the VO minimum operating condition. Okay, so this has to be because greater than 0.3. Okay. So an equivalent circuit مثل ما في عنا إياه بالBJT, Wilson designed an equivalent circuit for the MOSFET. He designed it in order to have a minimum number of transistors, okay, satisfying mainly the condition for a large output resistance. لأنه نحن بالموسفيت he wanted to satisfy the large RO. okay, which is achieved by stacking the two transistors on top of each other. نفس الكرنت حيقطع هون if these share the same VGS or the same VOV, the same voltage is shared, and if they are guaranteed in saturation, half K prime W by L VOV squared will be the same. حيقطع نفس الكرنت on this branch. Now the effective resistance, because of this diode connection, is not the perfect test code. We have it summarized on this sheet. It is GM3RO3 ضرب RO2 approximately, يلي هو a gain term ضرب little RO, which means it increases. It's close to that of the cascode resistance. So RO increases. Okay. Now, one thing about this is that, of course, the voltage range will be reduced. So the trick about this is that first, VGS1, so what is VO? VO هو عبارة عن VGS3 okay, plus VGS1 okay, and we want this to be greater than VOV, right? So sorry, this is and then greater than عفوا VGS3 minus VT. لا sorry, please ignore this. Sorry. Let me erase erase all 1 second. Let us repeat it again. Sorry, VO is really VDS3 plus VDS3 plus VGS1. Okay, let us type it in the regular. هلا بطلت. Okay, so let us type it here. Okay, so VO, let us erase this, move this out. So we have here, we want VDS3 to be greater than VGS3 minus VT. Okay, and VGS3 is equal to, okay, so this means that we want VD3 to be greater than VG3 minus VT. Now, VG3 itself is VGS3 plus VGS1, okay? So we want VD3 to be greater than VGS3 plus VGS1, okay? ونحن بنعرف كل وحدة minus VT, and we know that each one of these satisfies the VOV plus VT from the previous slide. So حيطلع عنا again 2 VO, okay? So therefore, whenever we have a stack of 2 transistors, typically we are going to have we will have 2 VOVs involved. Okay, so بيصغر الرينج تاعون ال VO ونفس الشيء حيكبر الريزيستنس that we have. Now, there was an improved balanced current mirror. Let us examine this little bit quickly. Typically, if I have a channel length modulation, حيصير ليطلع عندي نفس الكرنت بهيدا بده يكون عندنا نفس ال VDS باثنين. But this cannot be the case because this is not balanced. Okay, if you see this voltage from here to here really covers this part and covers this part also. So balancing or making VDS2, it is the same as VG3. So ما حقدر أنا أخلي perfectly VDS. We don't want to go into details for them to be equal. We are not responsible for this. Don't worry, it needs a blackboard to explain it. So اللي صار إجا قال ويلسون إنه let us put 4 transistors, لأنه with 4 transistors I can guarantee that I can have the same VDS across of all of them at some operating point, and I can guarantee that the channel length modulation factor can be cancelled. So it is more adding 1 more transistor in order to balance the drain voltages لصير اقدر خليهم يصيروا قد بعضهم, and therefore have eliminate if I can the channel length modulation. So this is a more balanced design. بعده عندنا stacked transistors, and so we still have a large RO. So for you, anytime you see a current mirror with stacked transistor, you can directly approximate it by the RXY resistance. This is what really matters for us. This we are going to analyze it a little bit more. This is another BJT current mirror, but this time this BJT current mirror is not intended to reduce the error term. It is mainly intended to allow me to generate very small currents IO without having to put large resistors in my circuit. So this is its objective. We will summarize it soon. And also, it has a high output resistance. It has a high output resistance. لأن if I assume this is DC, I am really looking through a BJT and a resistor at the emitter. So كمان رجعنا, we have the RO that is large. So let us first focus on the main reason for this circuit, which is having the small current capability. Let us see. نحن كنا نقول إنه if I want to size this circuit, I have to size it, or even for the BJT, I have to change some area in the device. بدي أطلع على IO على I reference. So here they start by telling me, let us start from the fact that those two have a shared VBE. So the first equation tells me that VBE1 is equal to VBE2 plus IE اللي نازلة هون ضرب RE, يعني plus this voltage. Okay? Now from the current equation of a BJT, I know that VBE is VT ln IC over IS. Let us ignore this one term because it comes from the reverse saturation current. Okay? So therefore, VBE1 equal VBE2 plus IE times RE. I replace VBE with its value اللي هو VT ln IC على IS. Let us assume that we remember this equation now. What can I do with those two lens? What is IC1? If I ignore beta, okay, and assume IC equals IE, okay, فيني اعتبر انه هاي تقريبا هي IE for the time being, okay. So if I ignore beta, the same current that is flowing here is also flowing where? In the collector. يعني فيني اعتبر IC2 هي IE2 هي what؟ أو sorry يعني هي IO. okay. And then what is IC1? إذا اعتبرنا بتا رايحة طايرة من هون بهالerror term, it is equal to I ref. مش هيدي هي IC1? So it is equal to I ref. So فيني اعتبر هيدي هي I ref here. Now I have two lens on both sides. So let us insert a new slide here. Okay, let us insert a duplicate slide and let us erase all of these below and let us type. Okay, so I'm going to insert a text box here and here. If I have ln of A equal ln of B plus C, I can bring it to the right, so it will be ln of BA. شو بيصير عندنا minus ln of B شو بيصير؟ بيصير ln equals C. It becomes ln of A over B equals C, right? So in a similar fashion, what is going to happen here is we will say that I will have VT times ln of, حنشيل الترم تاعون الماينس 1. ال A هي IC1 over reference, okay, اللي هي over IS عفوا, اللي هي I ref over IS, okay. Okay, هيدي حنقسمها على مين؟ We will divide it by who? We will divide it by IO over IS, okay, is equal to IE2 اللي هي IE2 حنعتبرها ضرب RE. حنعتبرها شو بتساوي ال IE2 ضرب RE؟ حنعتبر ال IE2 ضرب RE is equal to I-O ضرب R-A تقريبا. Okay, so let me try to write it in a better way. So here we have ln of, so this is VT times ln of I reference على IS حيطير ال IS in the two terms. So this becomes I reference over I. Okay, this becomes I reference over IO is equal to IO times RE. Okay, so let us go back to the slide and repeat the explanation on the original slide. Hopefully I can delete the, let us delete it from here. Okay, so now if we repeat this, okay, what we started with is that the VBE is equal to VBE plus IE on those two sides. Then we said that the VBE as function of IE is a logarithmic function. We said that this is my I reference, okay, here, and that this is approximately my IO, okay, because we assume that beta equals to 0. And then IE is also my IO as well. And we took this term to this side, the subtraction of a logarithm will give me the subtraction of a logarithm will give me the ratio of the two quantities, and now I have this relation which is VT ln of I reference على IO equal IORE. The trick is that if I am requesting from you that I want IO to be equal to 1E minus 6 amps, okay, whereas you know that I reference اللي قطع بالهيدا is equal to 1E minus 3. The ratio يعني 1 ملي amp. This ratio is now what? It is 1000. It is 1K, right? The ln of the 1K is a small number, and therefore I can now afford to have a small resistor to satisfy this quantity, because we are requiring, this is ln of 1K. مع انه هيدا الرقم مضروب ب 1A minus 6, I can now have RE to be small لأنه ln is the logarithmic number is a small number. Okay, so this allows me to establish small IO currents because of the logarithm that reduces the ratio. هلا كان بضطر انه يكون عندي كثير resistors اكبر. Does anybody have a question about this? Okay, thank you very much. Okay, so this concludes the part about part 3, which had current mirrors and amplifiers and high frequency response. Today in the afternoon around 5, we will have a meeting for the Q&A of the slides that I sent previously. Were you able to listen to them? Can you all type? The lectures which I sent by email last week. Okay, so in case you have a Q&A, I will be available to answer you around 5 p.m. if hopefully all is good. Thank you. And now we will move to the next section, part 4, which I think you are all familiar with, which is about the operational amplifier. So let me minimize this section and then open the other set of slides. Okay, so here's the thing. Why are we studying the operational amplifiers? You've seen the circuit before. Inside the circuit, there are a certain arrangement of transistors, which we will study later, which relies on the common source or the common drain, common gate combination to achieve this circuit. So the first step which we will do is we will review the ideal op-amp to see how it operates, where we benefit from in the different applications of communication, power, etc. And then we will open it up and say, well, let's look now this module or schematic or abstraction that we are studying here, really is designed this way. And here is how I can achieve a certain common mode, and here's how I can achieve a certain differential mode gain. Here's how I can get rid of the noise by designing my circuit. So I believe you've seen this maybe in 290, if I am correct, or some of the other courses. And the operational amplifier is really a circuit that has two primary inputs. It has a supply VCC and minus VAE, and it has one output node, which is a third node. One of the inputs is inverting, so you can see the minus sign here, and the other input is non-inverting. Okay? An ideal operational amplifier, and this is one key thing that we need to understand, has a certain gain A, it has a certain input resistance and certain output resistance. The ideal amplifier will have infinite input resistance, meaning the current that is flowing into those pins is equal to 0, okay? And it has 0 output resistance. You can see there is no loss here, no losses here. Ideally, A tends to infinity. Now, we can have ideal A, we can have A which is infinite, or we can have A which is finite, okay? So we always start with the ideal, where the currents are 0, the output resistance is 0, and A is infinite. If we tell you that it has finite A, only A is finite, you still maintain the current is 0 that is flowing into the branches. So depends what we tell you. Now, the key thing is that this has a gain A. But when we have this operational amplifier now, as we will see next and you have seen before, hooked up to some additional resistors and some voltage source, etc., and we are studying VO over VN, this whole thing will have another gain, A, op amp, let us call it op, which is also, although this has infinite gain, this becomes finite. So this is the open loop gain, okay? And this is the closed loop gain. And by closed loop gain, we mean that we have put some circuitry around my circuit, around my amplifier, and this circuitry, as we will see next, is going to adjust the gain, okay? And so we need to differentiate between them because this is something that the students typically confuse. So the open loop gain is the A that is given with the amplifier stand alone, and the closed loop gain is when I put circuitry around my amp. Okay? So typically, we know that from the configuration of the amplifier that V out is equal to A times V2 minus V1. Okay? This is the definition of the op amp, and this is the open loop gain, which is ideally infinite. Now, here they'll just tell me if VCC and VEE, let us say, reach 15 volts and minus 15 volts, nobody can generate power or energy. And that what happens is that the output will operate within this range. We cannot exceed it. Sometimes we operate a little bit below this range or within this range because of noise and because of constraints within the circuit. It is in the end an amplifier made of transistors with a current mirror with some VO min and VO max like we studied before. Now, another thing, if this is infinite, and I'm assuming things are ideal, and this is some number, then I have to assume that this is 0, because only when I multiply infinity by a 0, I will get a number. So if we say that the amplifier is ideal, this means that when A tends to infinity, and VO is a fixed number between plus 15 and minus 15, this forces a constraint on V1 and V2 to be equal. So we always assume in the ideal situation that V1 and V2 are equal when A tends to infinity. Okay? Anybody has any questions? Okay, great. So the first configuration of the amplifier is the inverting amplifier configuration, where I really have a ground at the non-inverting input, and I have a connection of Vn here, so this is Vn here, connected to R1 to node 1, and then node 1 is connected via R2 to node 3, which is the output. The first thing that we remember is that this current here is 0, so there is no current flowing into the amplifier. And the second thing that we remember, if this A is infinite, that V1 is equal to V2. Okay, so if V1 is equal to V2, this means that I have a ground here. So if this voltage is 0 here, this means I will have also 0 here. Okay, so we are going to assume now that node V1 is really a ground. Okay, so therefore I have here a ground. Okay, so this is also a ground. Now I will apply KCL. I know no current is flowing in here. So what does KCL tell me? It tells me that the current that is going into R1 has no other place to go but into R2. But the current that is in R1 is equal to VI over Vn. They call it Vn so that to differentiate from V little I. Vn over R1. Okay, this is equal to 0 minus V3 or minus VO over R2. So I already established a relation between VO and Vn, right? So if we derive this relation, we will find that the gain is equal to minus R2 over R1. Okay? So this is established relation. Now the second thing that I would be looking for is what is the input resistance. The input resistance is nothing but Vn over In, which is equal to Vn, which is equal to I1 times R1, right? I1 times R1 over I1, which is equal to R1. So the input R1, okay? The output resistance, don't worry about it now, okay? So therefore, we established for this circuit its gain and its output input resistance, okay? Now, the next question that comes to mind is that, well, what happens to the input resistance? If I want the input resistance to grow up, my gain is going to grow down. So there is a trade-off here for this circuit, but I have to live with it. And then the second question becomes, well, what if A is not infinite, A is finite? Then I will have to set V2 equal to 0. So we know that A times V2 minus V1 equals to VO. Okay, since V2 equals to 0, we will establish this relationship that VO equals minus A times V1, or V1 equals minus VO over A. The current flowing here is still what? The current that is flowing here is still equal to 0. Okay, so I still have the KCL setting that I1 equals to I2. Okay, and therefore, the only thing is that this will be Vn minus V1. So this will be Vn minus V1 over R1 equals V1 minus VO over R2. Okay, but I know that V1, I have already established it from this relation as function of VO. Okay, so I plug it in here, and I will get an equation that relates Vn to VO, and we will end up with a complex equation that looks like this. AV equal VO على Vn, which is equal minus R2 over R1 over this complex term, and this little a is the characteristic of my op-amp. Okay, when A tends to infinity, this whole term drops down to 0, and I end up with the term over 1, which is the term that we derived in the previous slide. Now, does anybody have any question about this amplifier? Okay, great. Okay, so on Wednesday, hopefully, we will continue with the remaining slides for part 4. In the afternoon, I will have a Q&A session just to get a vote of hands. How many of you will be attending this session or asking questions? Consider it office hours. I will still be there, hopefully. Okay, now if you I did not get too many responses. I did not get any responses actually. If you plan to attend, please send me an email or type yes now. Okay, I see a few hands raised. So I will be there for you for the session, and hopefully we can all get over this on study well. So hopefully it's a good experience. For the midterm, we still really don't know. Let us finish the material for the midterm first, and we are getting the directives from the president. I'm not sure, did you all get the email from the president yesterday? Don't be scared, just stay safe. Don't worry. We will study the material from home, and we will see what we can do for the midterm. Let us first grasp the material one slide after the other. And I will give you extra office hours for the material, okay? So we will not give you a midterm before we see you. And if we have to, I will give you too many extra office hours, don't worry, okay? Yeah, take good care, stay safe. That's what matters now. Take care, bye. Bye, bye. Thank you, bye.